All right, hi everyone, and welcome to our BARC's Wetland Mapping 101 training. This is the first part of a two-part training. The second part will be in the field. Great. If you are unfamiliar with BARC, welcome. We're glad that you're here. This is BARC's mission, which is to transform Mount Hood National Forest into a place where natural processes prevail, where wildlife thrives, and where local communities have a social, cultural, and economic investment in its restoration and preservation. You can follow us on Facebook or Instagram at Bark for Mount Hood, or you can go to our website at www.bark-out.org for more information. Can go next slide. If you've been to a recent BARC event, you've probably encountered our land acknowledgement practice. So we start every event with a land acknowledgement practice that we've developed. So we're going to start by reading this historical accountability statement, and then we will have more of like an interactive practice part of this. So you can read along with me. As an organization founded by white people in the lineage of settler colonial environmentalism, BARC understands that conservation work is embedded in the white supremacist legacy of colonization, land theft, cultural erasure, genocide, and the systemic use of law to suppress Native sovereignty over their homelands. We understand that BARC's dedication to protecting stolen lands, referred to now as the public lands of Mount Hood National Forest, carries with it this paradox, which continues to be ignored by most conservation groups, and which continues to harm Indigenous people today. In our advocacy and policy work, BARC's interactions with federal agencies often comply with the authority assumed by the U.S. federal government. This authority was assumed through the legalized displacement and genocide of Indigenous people and cultures, including through the legislative creation of public lands. These crimes and injustices have not been reconciled nor rectified. Today, all non-Native people have the privilege of primary access to these public lands as a direct result of this strategy of legalized supremacy. BARC recognizes that conservation organizations like ours are complicitly participating in the ongoing displacement of Native people and culture each time settlers and other non-Indigenous people claim the benefits of access to this land by engaging the paradox of protecting stolen land. We are working to change the vision, mission, and strategies of our organization. BARC affirms that these are the rightful homelands of the Multnomah, Molalla, Kalapuya, Chinook, Clackamas, Tenino, Wasco, Wishram, Paiute, and the many other Native people who live here and who have always lived here, who have always belonged to and cared for this land, and whose bold resistance to colonial oppression should guide us all. Now I would like to respectfully invite any Native people here today to have a few minutes to speak freely. If you would like to speak, you can go ahead and unmute yourself or type into the chat. BARC is committing to the work necessary to repair relationships between settler descendants and Indigenous people, and between all non-Indigenous people in the land. Acknowledgement is just the first step in this revolutionary cultural work. We ask all non-Indigenous participants to practice humility, respect, and acknowledgement by personally dedicating your time, energy, action, and resources to support the people who rightfully belong to this land. If you have practiced acknowledgement with BARC before, please get the notebook you use for this practice. If this is your first practice, please get something to write with. And I'll give everyone a few moments to do that before we start writing. Please take the next 2 to 3 minutes to write some instructions, intentions, actions, or next steps for yourself, outlining how you will develop your practice of acknowledgement through action. If you have been to a recent BARC event, please revisit what you have set out for yourself to do and take this time to reflect on your efforts and update your intention and action plan. Okay, now please set aside your journal. And we're going to turn our attention away from yourself, or turn your attention away from yourself. And please join me in a moment of respectful silence in contemplation and humility in honor of the original people here tonight, across this continent, in the past, present, and the future. Thank you all for supporting this important practice and learning. It is important that we continue to practice acknowledgement in all areas of our lives. And now we'll get the training started. My name's Misha. I'm BARC's Forest Watch Assistant, and I use they, them pronouns. That's my very short introduction. Michael and Kyla, would you like to?
Sure, I can go. Yeah, my name is Michael Krokta, and I'm BARC's Forest Watch Coordinator, and I go by he, him pronouns. And I'm really excited to be here tonight. Thanks.
I'm Kyla Zaret. I use she, her pronouns. And I will get started with the training and tell you a little bit more about me. All right, well, hi everyone. Thanks for your interest in wetland mapping and field verification. And thanks to Misha and Michael for making this training happen. I'm Kyla Zaret. I work as a wetland ecologist with the Institute for Natural Resources at Portland State University. And in that role and in partnership with BARC, I've been helping with the design and data collection for the beaver and wetland restoration project in Mount Hood National Forest. This online training and the field training are designed to provide information and tools so that volunteers like you can help achieve some of this project's goals. For one, we're working on an inventory of the types and locations of wetlands in the Clackamas District in Mount Hood. This is important because wetlands of different types have different ecological functions, such as providing plant, fish, or amphibian habitat, contributing to carbon or nitrogen cycling, or storing and releasing surface water during summer droughts. Before we plan restoration activities that will directly impact sites, we need to know what the trade-offs are between our specific restoration goals and the ecosystem services already provided by a site, and what could be lost by altering a site's structure and function. For example, though ultimately we're interested in increased water storage, and thus we're considering activities such as installing beaver dam analogs, we may not want to permanently inundate a wetland that is right now functioning as a biodiverse wet meadow, especially if there are only a few wet meadows in our target watershed. To complete the wetland inventory, we'll be editing and updating the National Wetland Inventory for our project area. National Wetland Inventory, or NWI, is a geodatabase hosted and managed by the U.S. Fish and Wildlife Service. It contains a spatial data layer of polygons that represent wetland boundaries, which you can see in white in the image on the right. We'll be using aerial imagery and the technique of photointerpretation to determine where the boundaries between distinct wetland patches or zones should be drawn and how they should be classified. A critical part of wetland mapping, since much of this is done remotely in the office, is field verification, and that's where we need your help. We're hoping that this summer you'll help us ground truth map sites to verify whether they are indeed wetlands and whether they've been classified as the correct wetland type. So today's objectives are to work on answering the following questions. How do we know if we're in a wetland? What type of wetland is it? To determine whether we're in a site that should be considered a wetland, we'll review our working definition of wetlands and look at examples of wetland indicators that you can observe directly in the field. And to figure out wetland type, we'll walk through the coordinate classification system, the classification system used by the National Wetland Inventory, and we'll talk about what we can infer about wetland types by interpreting aerial imagery, as well as through direct observation on the ground. Please keep in mind that our overarching goal is to start to prepare you to conduct fieldwork using some key concepts and tools. These include the Wetland Field Verification Data Sheet, which we'll look at briefly today, but we'll spend much more time with during the field training. There's going to be a lot of detail coming up, especially when we talk about the classification system, but please don't feel like you need to take it in, that you don't need to take it all in right now. So let's start with the question, what is a wetland? For folks who are able to watch the Introduction to Wetlands video, this will be a review, but there are some points that I want to highlight. When we think of wetlands, we often think of places with standing or ponded surface water. Some wetlands are indeed permanently flooded, like cattail marshes or Sycamore spruce swamps, and others are characterized by water tables that are very close to the surface, like bogs. However, most wetlands are not permanently inundated and may in fact be dry for much of the year, like forested bottomlands, vernal pools, or the wet meadow pictured here. How can we define wetlands if not by water presence? The answer isn't straightforward. According to the manual titled Classification of Wetlands and Deepwater Habitats of the US, there is no single, correct, indisputable, ecologically sound definition for wetlands, primarily because of the diversity of wetlands and because the demarcation between dry and wet environments is dynamic and lies along a continuum or gradient. This gradient of wetness can make wetland boundaries difficult to distinguish from other types of ecosystems. In general, we can think of wetlands as occupying transitional zones between terrestrial and aquatic environments, shown here on the left by well-drained forested uplands, and on the right by permanently flooded deep water habitats. Like wetlands, riparian areas are also transitional zones. Boundaries that separate riparian areas from uplands or wetlands can be subtle, but riparian areas are almost always associated with a well-defined stream or river channel. So how do we know whether a site is a wetland? For our purposes, and since we'll be ground truthing sites that are mapped using the NWI's coordinate classification system, we'll be working with an ecological rather than a regulatory or jurisdictional definition. Thus, we'll be looking for the presence of at least one of three defining components of wetlands: water, whether current or recent, hydric soils, and hydrophytic vegetation. In the next slides, we'll look at each of these three components in turn, but keep in mind that they're interrelated. For example, site wetness is dynamic. It can change a lot across a single growing season. A site may be fully inundated in the spring, but totally dry by midsummer. However, soil properties and plant communities change more slowly, and they reflect the prevailing degree of wetness at a site over time. When we talk about wetland hydrology, we're especially interested in the amount and pattern of water presence, because these factors determine whether a wetland is formed and maintained at a given site, as well as the type and functioning of the wetland. The term water regime is used to summarize the amount and pattern of water presence. A wetland's water regime is characterized by the depth, duration, frequency, daily fluctuation, and seasonal timing of precipitation, surface water, and groundwater. In other words, water regimes summarize when, how, and how often water arrives at a site, how deep that water gets, and how long it stays. The vernal pool shown in the photos on the left can be said to have a seasonal water regime. It fills with rainwater in the spring, dries out by the end of the summer, and again fills with rain come the fall. Now let's think about wetland hydrology in the context of fieldwork and trying to determine whether a site is a wetland. How can we tell whether a site was recently inundated or saturated by water if no water is currently present? Or how can we tell how much of a site has been covered by water? The answer is that we can look for the following indicators or signs of wetland hydrology. For example, we can look for algal mats or crusts. These are mats, crusts of dried algae left on or near the soil surface after surface water recedes or evaporates. We can also look for iron deposits, thin orange or yellow crusts or gels of oxidized iron on the soil surface or on objects near the surface, like rocks, plant roots, and woody debris. Cracks in the soil surface are another indicator of recent inundation, but note that these are most likely to form in certain types of soils, like clayey soils, and not so likely to form in organic soils. A fourth indicator is water-stained leaves. These are fallen leaves or leaves that died in place that have turned grayish or blackish in color due to inundation for long periods. And one final note, besides these visual clues of recent water presence, if you smell hydrogen sulfide or rotten egg odor as you walk across the site, it's a pretty good sign that the soil is currently or was recently saturated. Now let's turn to hydric soils. Hydric soils are defined as soils that are water saturated for extended periods of time during the growing season. Soils that are waterlogged will often demonstrate characteristics that distinguish them from non-hydric soils. In non-hydric soils, oxygen is trapped in the many pore spaces between soil particles, but in hydric soils, oxygen in pore spaces are rapidly depleted and anaerobic conditions result. This lack of oxygen affects biological and chemical soil processes. For example, since plants need oxygen to carry out respiration, if anaerobic conditions last for just a few weeks during the growing season, most upland plants will die. As discussed later, wetland plants have adaptations that allow them to survive under the low oxygen and nutrient poor conditions of wetlands. So what do hydric soils look like? The photo on the left illustrates one characteristic of hydric soils, mottling. Mottling refers to the presence of different zones of color and texture within a soil sample that's caused by periods of saturation, followed by periods of drying out, or aeration. The photo on the right shows two types of organic soils. Organic soils develop in wetlands that are saturated for much or all of the year, and that's where rates of decay are very slow. Peat soils are a distinguishing characteristic of wetlands that we call mires, bogs, or peatlands. So what about soils in the context of our fieldwork? As you can see from the photo on the right, soil sampling can be quite an involved process. We don't expect you to be doing intensive soil sampling this summer, but you'll primarily use the indicators of wetland hydrology and wetland vegetation to figure out whether a site should be considered a wetland ecologically. However, BARC does have a couple of soil augers that you can borrow, and looking at even just the top layers of a soil profile can yield clues about a site's water regime. For example, extracting a bite of soil can help you determine whether the soil is saturated. That is, when you break open that bite of soil, you'll see water glistening on the newly exposed areas. If it's mid to late summer and the soil below ground is saturated, while the surface is dry, you have some evidence that the site is groundwater fed and thus may stay wet until the end of the growing season, or even year round. Soil texture can also be revealing. The presence of organic rather than mineral soil also suggests long-term water presence, and so you know that a site wasn't only briefly inundated during the start of the growing season. The presence of redoxomorphic features in mineral soils also tells us something about water regime. Redoxomorphic features give soils a mottled look. They include yellow, orange, or red masses that are accumulations of iron. As soils become saturated and oxygen is depleted, iron reduces and moves into the water column and through the soil profile until it hits a zone of oxygen, like around plant roots, and then it precipitates out. The presence of redoxomorphic features suggests water fluctuation, such as in sites that mainly exist as wetlands due to the capture of precipitation. These sites often have clayey soils with very fine pore spaces that fill quickly with water, such that rain or snowmelt accumulates on top of the soil until evaporation or transpiration by plants draws the water level back down again. And finally, I want to mention that some mineral soils that are inundated for very long periods of time may not have any redoxomorphic features. Instead, they have a uniform light gray or clay color, as in the middle bottom photo, that indicates the nearly complete reduction of iron. If you're interested and want to learn more about wetland soils, check out the NRCS technical report, Field Indicators of Hydric Soils in the United States. And also, I'll plan to demonstrate soil sampling during the field training. Moving on to hydrophytic vegetation. In addition to the criteria already described, wetlands are distinguished from uplands by having an abundance of plants adapted to growing in wet soils. Wetland plants are hydrophytic or water-loving and have adaptations that allow them to occupy saturated anaerobic soils. There are nearly 7,000 plant species in the US that may occur in wetlands. While non-wetland plants take in oxygen through the roots and distribute it to the stems and leaves, in saturated soils, wetland plants need to use other strategies. Having these and other adaptations allows wetland plants to survive, thrive, and even outcompete other plants in these environments. Let's take a look at some examples. Cattails, sedges, and rushes all have oxygen transporting structures in their stems. These specialized tissues are characterized by large air-filled cavities that allow for the exchange of gases between plant tissues above and below water. Other adaptations of wetland plants include changes in growth form that maximize the amount of surface area exposed to air. These include adventitious roots, shallow roots, multiple stems, and roots close to the surface, like in cottonwoods and willows. Other plants have specialized nutrient capturing strategies. Carnivorous plants, such as pitcher plants and sundews, are particularly common in peatlands because acidic conditions limit the availability of nutrients. The ability to trap and digest insects provides a supplemental source of nitrogen. How can the vegetation of a site help you determine whether it's a wetland? For the purposes of wetland identification, plants are categorized according to the probability of occurring in wetland soils. 5 widely used categories have been developed. Facultative upland plants can survive in uplands or wetlands, but they're more likely to be in uplands. Plants that are facultative are those that have about an equal probability of appearing in uplands or wetlands, and facultative wet plants are more likely to be in wetlands. Obligatory wet plants are found only in wetlands. In Oregon, there are almost 600 plant species that have FAC wet or obligate status. You can use the US Army Corps of Engineers website shown here to look up the wetland indicator status of specific species. And we've also created an Excel spreadsheet that you can download, which lists Oregon's plants and their indicator statuses. That document is linked to the wetland field verification datasheet. But what if I'm not a botanist, you may ask? Well, I encourage you to start paying attention to the plants that are dominant in the wetlands and other beaver sites that you visit this summer. You could also start to study up on the types of plants and plant families that are commonly found in wetlands. For example, in terms of trees, get to know alders, spruces, and lodgepole pine. Spruces and lodgepole pines can often be found growing in isolated clumps and peatlands. So if you're in a wetland with a carpet of moss and there are scattered individuals or islands of either of these tree species, there's a good chance that you're in a site that stays saturated year-round. For shrubs, learn to recognize Douglas spirea, willows, and bog laurel. And finally, get to know your graminoids. It's especially helpful to be able to distinguish sedges and rushes on the one hand from grasses on the other, since the former are commonly found in inundated environments, whereas only certain grass species can tolerate wet places. You'll use much of the information that we just went over regarding the 3 defining components of wetlands to fill out part 2 of the wetland verification data sheet. You can see that the first question, Q1 at the top, asks whether the site you're visiting contains a wetland. To figure that out, you'll want to walk back and forth across the site, not just on its edges, and look for the listed indicators of current or recent water presence and hydrophytic vegetation, checking all that apply. You may note that we didn't explicitly include soil indicators beyond saturated soil, but you should feel free to write any extra observations in the notes section at the bottom. So I'm just going to pause here for the first round of Q&A. So the first set of slides introduced what wetlands are and how to start to tease out whether you're in a wetland in the field. And now we're going to turn to wetland classification, or getting at wetland type. Just as there are a variety of wetland definitions to suit different purposes, from regulatory to inventory and assessment, there are also a variety of different ways of classifying wetland ecosystems. These vary from classifications that are widely applicable across geographies to those that are specific to a given state or ecoregion. In addition, wetland classifications can be based on characteristics that encompass landscape position to those that key in on the species of plants that define a wetland community. As I mentioned earlier, we'll be focusing on the coordinate classification system, because this is the system we'll be using to map wetlands in the office, and thus the wetland types that you'll be ground truthing in the field. The coordinate classification system is the standard classification system for wetland mapping across the US. The system was first developed in 1979 by Coordinate et al. And revised in 2013 by the Federal Geographic Data Committee. To date, national wetland inventory mapping has been completed for most of the US, including Oregon. However, the majority of mapping in Oregon occurred in the 1980s or earlier, as you can see in the map on the right. Thus, the NWI doesn't fully represent the number, types, or boundaries of wetlands remaining today. In addition, the original NWI mapping was based on relatively low resolution base imagery, leading to mapping errors. This is why our project on wetland and beaver restoration in Mount Hood National Forest includes the goal of updating the NWI mapping for our project area. As we talk about coordinate, keep in mind that this classification system was developed to map wetlands as well as deep water habitats, including streams, rivers, lakes, and reservoirs. And it now also includes riparian areas. As an overview, the coordinate wetland classification system first separates wetlands into major systems, and then separates systems into subsystems, classes, and subclasses. To those, water regime and special modifiers are added. All of those components are captured by a coding convention built of letters and numbers, which is assigned to each mapped wetland. These letters and numbers ultimately represent the broad landscape context of the wetland, its vegetation structure, its water regime, and any natural or anthropogenic modifications to the wetland. Before we start to break this down, please note that the next slides are busy and full of detail. But remember, this is just a first pass at getting to know the coordinate system. There are lots of great resources to help apply it in the office in the field, and we'll be doing a bunch of practice. First, coordinate delineates 6 major systems, including marine, estuarine, riverine, lacustrine, palustrine, and riparian. Today, we're going to focus on the palustrine system to help keep things simple, and also because the majority of the sites that we're targeting for fieldwork are palustrine sites. Most palustrine wetlands are non-tidal wetlands that are dominated by trees, shrubs, and persistent emergent vegetation, including graminoids and forbs. Here, the term emergent refers to the herbaceous plants with erect stems that are rooted in a substrate, not free-floating. Palustrine wetlands also include those that are lacking in vegetation, but in that case, they need to be less than 20 acres in size, and the deepest part of the wetland should be less than 2.5 meters at low water. Palustrine wetlands don't have subsystems, but there are classes and subclasses. Palustrine classes include rock bottom, unconsolidated bottom, aquatic bed, unconsolidated shore, emergent, scrub shrub, and forested. Let's take a closer look at these. The first 3 classes are our ponds. They differ in terms of the nature of their substrate and the percent cover of their vegetation. So for example, rock bottoms and unconsolidated bottoms have less than 30% vegetation cover, and the former has a substrate of boulder and bedrock, while the latter has mud, silt, or gravel. In contrast, aquatic beds have more than 30% vegetation cover that's growing on or below the water surface. The palustrine class unconsolidated shore often applies to the shoreline around ponds, but it can also be used for some vernal pools as well as snowmelt depressions. Unconsolidated shores are characterized by having less than 75% cover of stones, boulders, or bedrock, and by less than 30% vegetation cover. As for our more familiar wetlands, these are dominated by emergents, shrubs, or trees. These coordinate classes are determined by the height of the tallest vegetation layer, and in each case, vegetation cover must be more than 30%. So for a palustrine emergent wetland, sedges, rushes, grasses, and or forbs need to form the tallest layer. Palustrine scrub shrub wetlands are those where the tallest vegetation is woody, but less than 20 feet tall, and forested wetlands are dominated by woody vegetation greater than 20 feet tall. National mapping standards only require that subclasses be used for palustrine emergent, scrub shrub, and forested wetlands. For these, subclasses are based on the persistence and structural form of a wetland's vegetation. For palustrine emergent wetlands, vegetation is considered persistent if the stems and leaves of the wetland plant are evident all year long above the surface of the soil or water, even if they're dead. But they're non-persistent if there's a dormant period with absolutely no sign of emergent vegetation. For scrub shrub and forested wetland, vegetation is characterized as either broadleaved or needle-leaved, and deciduous or evergreen. So let's put together what we've learned so far about the coordinate classification system. Take a look at this cattail marsh. It's palustrine because it's non-tidal, dominated by emergent vegetation, and the area of open water is less than 20 acres. The class is emergent because the cattails are non-woody, they make up the tallest vegetation layer, and their cover is greater than 30%. The subclass is persistent because live or dead cattails remain throughout the year. Now, something that I didn't mention before is that a single wetland site can have more than one coordinate code. If there are distinct zones that are at least 5% of the wetland area, then different coordinate codes can be applied to each zone. So for this palustrine marsh, we can delineate a second coordinate zone around the area of open water with what looks to be algae scattered on the surface. And we can call it an aquatic bed class with an algal subclass. Thus, this wetland has the coordinate codes PEM1, palustrine emergent persistent, and PAB1, palustrine aquatic bed algal. So far, we've looked at the parts of the coordinate classification system that capture a wetlands landscape context, whether it's palustrine or associated with a river or lake, and the structure of the vegetation as well as what we've looked at. But we can also add water regime modifiers to represent a wetland's hydrology. These modifiers contain information about the duration and frequency of flooding of a wetland. The class of wetland determines which water regimes may be applicable. Here, I'm only displaying some of the wetland classes that we've talked about. For aquatic beds, water regimes may be classified as seasonally flooded, semi-permanently flooded, intermittently flooded, etc. There are even more options for emergent, scrub, or forested wetlands. As we advance through the alphabet, the water regime letters represent more persistently wet conditions. From A, temporarily flooded, which could be the site is inundated only 2 to 3 weeks during the growing season, to H, permanently flooded, or flooded across the entire year. I'm not going to spend a lot of time defining all of the water regimes right now, but we'll come back to this later and we'll discuss water regimes in the field. And you can also read about these in the links provided in the wetland field verification data sheet. For now, let's look at some more examples of how coordinate codes can be applied to different sites, this time using water regime modifiers. Let's go back to our cattail marsh. So to determine which water regimes apply to a site, we need to use the clues that we learned earlier about figuring out a wetland's hydrology. Here, focusing on the cattail or PM1 zone of the site, we should consider the time of year when we're visiting. If it's June and we notice that there's already very little surface water under our feet as we move through the cattails, there's a good chance that the zone will dry up by the end of the summer. So for this part of the wetland, we'll add a C, or seasonally flooded water regime modifier. This PEM1C code tells us that this zone of the clustering wetland is emergent, persistent, and seasonally flooded. What about the other zone? Given that the water level is already drawing down quite a bit in the cattails, the fact that the water in the aquatic bed is still at the top of the depression or channel makes me think that perhaps it's groundwater fed, and thus will stay as wet throughout much of the year. So I'm going to add an F, or semi-permanently flooded modifier, to the coordinate code for that zone. The PAB1F code tells us that this portion of the clustering wetland is characterized by an aquatic bed, at least a portion of which is covered by algae, and that it's semi-permanently flooded. Okay, so now let's take a look at the tools you'll have to help you figure out coordinate codes in the field and how you'll be recording those in the wetland field verification data sheet. At the top of the data sheet, there's a list of equipment and references to gather before you head out to the field. Looking at the list of references in the orange box, the most important of these are starred, and they include a copy of the 2013 version of the Coordinate Manual, Classification of Wetlands and Deepwater Habitats in the US, and they also include a PDF with a variety of compiled resources that's titled WVC Select Resources. The WVC Select Resources contains things like the NWI Wetlands and Deepwater Map Code Diagram, which has charts for each of the systems, as well as water regime and special modifiers in the blue box in the bottom. The Select Resources also include some extracted pages from the Coordinate Manual, which describe the water regime modifiers. We'll spend more time with those resources in the field, but now let's take a look at the data sheet. In part 4A of the data sheet, you're asked to record observations, photos, and description for each coordinate zone that you identify in the site. To help you choose coordinate zones, part 4B on the next page includes a handy worksheet. This worksheet is meant to be used after you've wandered through a site looking for water, vegetation, and perhaps soil indicators, and when you've already decided that the site indeed contains a wetland. At that point, you want to start to record observations of different coordinate zones that cover at least 5% of the site. Remember that coordinate zones represent unique combinations of vegetation structure and wetness. For example, emergent vegetation with a seasonally flooded water regime would be distinct from emergent vegetation with a temporarily flooded water regime. You can use this worksheet to walk through the different components of the coordinate classification system to figure out the final code for each zone. We're going to give that a try using another example, but this time I'm going to ask for your input. So if you have the data sheet available and you can click on the WVC Select Resources link, please do that now and scroll to page 4, which has the NWI map code diagram with the clustering chart. And I'll give you just a minute to find that if you can. So here's a site that's somewhat more complex than the cattail marsh we looked at earlier. Like that site, this one is plustron because the open body of water is less than 20 acres and less than 2.5 meters deep. And the subsystem is NA because it's plustron. But what about the classes, subclasses, and water regimes? First, let's break it out into zones by vegetation and wetness. I see 4 different zones in this wetland. I see a zone of open water, a zone of orange graminoids along the shore, a zone of shrubs, and a zone of shorter green graminoids furthest from the water. The open water zone doesn't have any vegetation, and I'm going to assume that its substrate is mud or silt. So the class of this zone is unconsolidated bottom, and the subclass is mud. For the water regime, I'm going to interpret the absence of vegetation as an indicator that it stays relatively deep for most of the year. So I'll choose the permanently flooded modifier. So the first zone is described as a PUB3H, or plustron, unconsolidated bottom, mud, permanently flooded. Now let's look at the zone of orange graminoids. We're still in a plustron system with no subsystem. But what do you think about the class and subclass? And do you have some guesses as to the water regime? So take a moment to think about this and put your answers in the chat.
We've got a couple of guesses for emergent.
Very nice. Any guesses? Yeah.
Drew says, oh yeah, emergent and C for water regime, which is seasonally flooded.
Yeah, I like both of those. I think that these are likely sedges or rushes, which are rooted in the substrate. And I guess that they're going to persist even as they die back, which we may be starting to see here. And also, given their location along the shore, I think that they're going to be seasonally inundated by water as the pond rises. So I also agree with that C, seasonally flooded. So this zone gets a PEM1C for plustron, emergent, persistent, seasonally flooded.
And just really quick, want to clarify, someone guessed EMP, and just want to make sure that you know so the P was under the saltwater tidal regime. So when you're looking at like the water regimes, just make sure that you're looking at the ones that actually fit for the like initial category too. I don't know. Yeah.
Thanks for pointing that out. One of the resources that we haven't looked at, but that's in the select resources packet, is a table that lists for each class which water regimes are possible. And so again, we'll spend a bunch of time with that in the field. So let's do one more. This time, the zone dominated by shrubs. So let's pretend that these are willows and that after we've walked around in these willows, we haven't found any standing water or evidence of recent inundation. However, we know that willows are commonly found in wet places, and we see that the outermost zone is dominated by grasses that are much more green and vibrant than those in the uplands on the far shore. What coordinate code would you assign to this zone? So again, we're in the shrub zone here, and again, I'm curious about what you think of the class and what your guesses are as to the water regime.
Right, we've got one guess for SS1B, PSS1B, and B is seasonally saturated.
Yeah, I think I definitely agree with that SS1 being broadleaf deciduous for our willows. And then I was guessing A, but I think seasonally saturated is also possible. I think I'd probably want to walk around a bit more, and I'd probably want to take a look at the soil, especially if I saw like a hunk of organic matter. That's when I'd start to think about saturated. Given that right now there's no evidence of inundation, that's leaning me more towards the A, but definitely could be B as well. Nice.
Kyla, could you talk a little bit more about saturated versus flooded or inundated and what
Yeah.
that means?
So saturated means that all of the pores of the soil are full of water to the point where that soil is going to be glistening or looks like it's sweating. That is when you like crack open a bite of the soil, not just looking at the top. And inundated means that we actually are going to have some like standing water on the top of that soil. So what are some more questions that have come out of looking at Wetland classification so far?
Yeah, so this is not something that I think is required for the data sheet purposes, but when you were talking a little bit earlier about looking at soils as an indicator for groundwater, so water being persistent in the wetland throughout the year due to the presence of that groundwater, I'm wondering if there are any common signs maybe related to vegetation or any other indicators that the site might be groundwater influenced?
Yeah, I think so. The landscape position, coupled with the time of year when you're visiting the site, will definitely help give some understanding of whether groundwater is the main source of water. So water sources can be precipitation, such as rainfall. There can be surface flow, such as via snowmelt over land. There could be overbank flooding from any streams or rivers, or sort of flooding out from a pond or lake. And then there can also be groundwater. And so, especially if we're in a pretty dry part of the summer, and yet you still have saturated conditions. So often when there are saturated conditions at a site, you're going to observe a ground layer of moss. That's a really good indication that water's there over a long period of time, that the water table is really high near the surface, but it may not be above the surface. So you may not see inundation, you're seeing that saturation. Often in the wetlands on Mount Hood, we'll see shrubs such as bog laurel, we'll see huckleberries, and we'll see some other types of shrubs that are kind of short in stature. And that's also, those tend to be in groundwater systems along with graminoids. So a system dominated by sedges, rushes, and the occasional short statured shrub, I would say, is another good indication of groundwater. And especially if there isn't a water source such as a stream or river, and if it's been a long time since it's rained. Yeah, Misha, have I missed other things that you've learned about recently?
No. Yeah, there's like a bunch of questions that just popped into the chat, so I'm gonna move on to those, and also a clarification that graminoid are grasses. Okay, so we got one question says, are most of the classifications going to be for such small areas? Is that the nature of wetlands or just the frame of the pictures?
Nice. The classifications, so we are looking for we're looking at zones or patches of different sites. So if you spend a bunch of time walking around a forest, you've probably entered and exited patches that may be dominated by old growth, and then you get into a zone that where you have maybe regrowth following a fire or regeneration after logging. And so those are two distinct patches on the landscape, but they're forest patches. So in the wetland, we're looking for these wetland patches. And again, we're looking for these unique combinations of vegetation structure and water regime. And we want, again, that area that we consider a patch to be at least 5% of the site. And so the size is kind of going to vary depending on the total area of the site. The place that we'll be visiting in the fields, kind of a large wetland complex. I can't tell you the acreage right now. But you'll see there can be a lot of different coordinate zones, creating kind of a matrix or mosaic of different patch types in that kind of site.
We've got another question. Oh.
And sorry, I just want to clarify. So graminoid means it captures carices, it captures rushes, sedges, and grasses. It captures that whole group.
Another question is, could you explain persistent and non-persistent once more?
Yeah, so persistent for the purposes of the coordinate system means that there's some evidence, there's some sign of vegetation, that emergent vegetation. So our sedges, rushes, or grasses, or forbs. So strawberry, violets, other wildflowers are examples of forbs. So all of those, there's some sign of them left around that you can see. That's persistent. And non-persistent, which I really don't think we're going to run into, it means that there's absolutely no sign of the vegetation. And so really this comes more into play when we're mapping. It's going to be harder to know that in the field unless you visit a site multiple times. So when we're mapping, as I'll talk about a little bit in the future, I'm looking at multiple imagery years. And so if 1 year of imagery, I see a bunch of sedges, and in another year, there's absolutely no vegetation, then I'm going to call that non-persistent.
And then the last question we have is, what are the main ways to distinguish between water regimes?
Yeah, I don't know if I can give you the main ways, but it's really thinking about the interactions between sort of all of the properties of the site that we've talked about and that we will talk about. So we can start off at the landscape context. We're thinking about, is this a site that's capturing precipitation? So is this kind of a bowl-shaped site where likely water is to fill up and not run out? Is this a site that's located against a slope? Because that slope breaks. If there's a really steep slope and then we hit this flat of the wetland, often groundwater emerges at that slope break. And when there's groundwater, usually groundwater sticks around longer into the season than the effects of precipitation. So that's going to help us make some calls about water regime. Besides landscape context, again, we're thinking about the vegetation that's there. Is it a facultative plant that can handle wet conditions, but it really prefers when conditions are dry? That will help us figure out what's going on in terms of how long water stays on the site. And then that soil. So a soil that has a whole bunch of organic content also suggests water's around for quite a while. And then honestly, like with many things, it's kind of experience. So the more sites you see, the better understanding you get of differences between sites. And that's going to help you narrow into some of the subtleties between water regime types. So spend time out there looking at these different places, and you're going to start to get a sense of water regime.
The other thing about the water regimes that I found was like sometimes those words aren't very clear about how much time they have, but the explanation describes it, so we can look at that more when we're in the field. Yeah.
Yeah, I really encourage everyone, if you can take the time, do look through the resources that are in that PDF packet, and read through them. That'll help, because also the more times that you're exposed to that language, the more it will be in your head too, and then we'll have more opportunity for discussion.
And then another question is, when do you split a wetland into different coordinate zones instead of lumping it into one?
Yeah. So when I'm mapping, a zone has to be at least 0.5 acres in order to be mapped. That's the minimum mapping unit. So anything smaller, I'm not going to pick it out from the rest of the wetland. And that's going to be something that's a little harder to do in the field since you don't have as much of a sense of scale. But in general, in terms of thinking about mapping as well, we try to kind of lump patches as much as we can. We're trying to reduce the amount, like basically the amount of data that's in the geodatabase to some extent. And then we could talk about some of the trade-offs. So for like data management purposes, it's kind of great to lump in terms of inventory purposes, and we want to know like more about what's happening on the ground. Maybe we want to pull out more individual patches to have a better sense of what's really going on with the ecological dynamics of a site. But I think it might be easier to talk about this in the field. Okay, so the last part of the training, I want to briefly touch on wetland photointerpretation. So what can we observe or infer about wetland structure and wetness from aerial imagery? First, here are some of the elements that we can detect visually in air photos and satellite images. These include shape and size, tone, color, and brightness, texture, and pattern. All of these elements come into play when we map wetlands. So here's an image of the Clackamas Lake site that we'll be visiting. This image was taken in August of 2018. It's of 1 meter resolution, and it's in true color, which means that the greens are green and blues are blue, etc. We can see how the borders of the wetland readily stand out given the different sizes and textures of the forest trees versus the wetland plants. We can also see the patterns made by the channels. These guys, and we can see easily the blue of the pond. And finally, we can see modeling of greens and browns across the site. So over here where my cursor is, I actually am seeing like a little bit of yellow. I'm seeing some darker green in this middle section, and I'm seeing a whole bunch of modeling of brown and green. So these changes in color and tone may indicate different zones of vegetation and wetness. Often when we're mapping wetlands using aerial imagery, we work with multiple sets of imagery, both true color and color infrared. In color infrared or CIR imagery, greens become red, and the brighter the red, the more vibrant the vegetation. Also, water tends to be teal blue or gray to black in color. So despite all the modeling in the true color photo, when I look at this CIR photo, I don't see such strong variation in color and tone. That makes me think that while there are different patches of vegetation, maybe different species of sedges dominate different portions of the site, these patches don't seem to vary in terms of their wetness or water regime. So looking at these 2018 photos, I may be tempted to map only a couple of coordinate zones, one for the open water pond and one for the rest of the emergent vegetation. But I see a really different story when I look at different imagery years. Often when I'm mapping wetlands, I'll scroll through true color and color infrared imagery for 6 or more different years for each potential coordinate zone. So here we're looking at imagery from 2009, which was a much wetter year. I say that because the width of the channels are wider than in the 2018 imagery, and I see patches of surface water and soil saturation amidst the emergent vegetation. These patches are brown in the true color image, and they're gray in the CIR image. So for example, in the true color, in both of them, I'm eyeing this kind of brown section here, and I'm seeing this as surface water. So that kind of smooth brown, even brown to me is surface water. Whereas here in like the middle part of the site, the brown there may be more saturation. And here in the true color or the color infrared image, again, I'm seeing fairly even color of gray, though this darker area in the center may be a deeper, maybe a pool of water. And then I'm seeing things like this modeling here on the left, some more modeling towards the top of the site. So my mapping ultimately looked like this. I used the most recent imagery year as the base layer for drawing the boundaries of my polygons, but I interpreted what I was seeing using all of the available information, including from 2009. So thus I have both PEM1Cs, throughout much of the site. So here, my cursor, here in the center, here on the right. So again, those PEM1Cs are palustrine, emergent, persistent, seasonally flooded. But I also added a few zones of PEM1Es. So here in the CIR in 2018, and then on the left here in the true color, and this was 2009, again, where we can see standing water here in 2009, but in 2018, it's drier. And I think that saturation was visible in 2009 because the site stayed wetter later, but in the 2018, the water table had probably drawn down in those patches by the time the photo was taken in August. And so we'll spend some more time looking at this imagery as we walk around the site in the field and talk about more of how we can use these maps to help guide where you're making observations in, as you walk through the data sheet. And remember, what we're doing with field verification is verifying the mapping. So with this aerial imagery, I wanted to give you a sense of the decisions I'm making and what I'm seeing as I'm placing these polygons. And then when you're in the field, I'm hoping that you're going to visit this PEM1C and give us a sense of whether you think that's right. And then you're going to wander over here, hopefully get into this PEM1C and see if that holds over there. And then you might wander into this PEM1E and see if that looks like it's the correct coordinate code. All right, well, that's what I have for you for right now. Please ask some more questions if you have them, and if not, bring them to the training in the field.
Yeah, thanks so much, Kyla. So yeah, we do have a little bit of time now for questions if folks have some more. Yeah, I just want to again remind everyone that we're going to be picking up part 2 of this on Sunday at Clackamas Lake, which is what this is an image of. Or at another time, if you're signed up and you're still on the wait list. We had to limit the group size for safety reasons, but it's, you know, not to worry if you're here tonight and you couldn't get into the training. Just keep an eye out in case things open up, because oftentimes they do, and we'll email that out to folks. And then there's going to be a lot more opportunities to put what you learned tonight into practice throughout the spring and the summer. And, you know, along with all the resources that Kyla shared, we're also going to be providing maps of all the sites and, you know, providing you with everything that you're going to need for each of these field days where we go out. So we'll just give a couple minutes now for questions if anyone has any.